Welcome, and thank you for joining me. I'm so glad you're here. Before we start, I'd love it if you could share in the comments where you're watching from and what time it is for you right now. It's always fascinating to see the range of times and places represented here. Thank you also to those who continue to subscribe and show their support with likes. It really guides me in shaping this space and helps others discover it too. If you have ideas for future videos, please let me know in the comments. With that, let's begin. Chapter 1: Understanding Subatomic Particles and Forces. In the vast expanse of the universe, beneath the swirling galaxies and the shimmering stars, lies a world so small that it eludes the naked eye. This world is the realm of subatomic particles, the fundamental building blocks of all matter. Imagine the intricate structures of everything you see around you, from the tallest mountains to the tiniest grains of sand. Each object, each living being, is composed of atoms, which in turn are made of even smaller entities: protons, neutrons, and electrons. Protons, with their positive charge, reside within the nucleus of an atom, alongside neutrons, which carry no charge. Together, they form the heart of the atom, a dense core that provides stability and structure. Electrons, on the other hand, are nimble and elusive, zipping around the nucleus in a cloud-like formation. They possess a negative charge and play a crucial role in the chemical properties of atoms, determining how they bond with one another to create the myriad substances around us. As we ponder the nature of these particles, we cannot help but marvel at their remarkable characteristics. Protons are not merely static entities. They are composed of even smaller particles known as quarks, held together by the strong force, one of the four fundamental forces in the universe. Neutrons, too, are made up of quarks, showcasing the intricate and layered nature of matter. The strong force is indeed a fascinating concept, as it binds quarks together within protons and neutrons, overcoming the repulsive electromagnetic force that would otherwise push similarly charged particles apart. This force operates at incredibly short ranges, but its strength is immense, allowing atomic nuclei to exist in harmony despite the repulsion between protons. Can you imagine such potent forces working tirelessly to maintain the balance of the universe? Then there is the electromagnetic force, a critical player in the interactions between charged particles. It governs the attraction between electrons and protons, ensuring that electrons remain bound to the nucleus. This force is responsible for the myriad of phenomena we encounter daily, from the way objects stick to one another to the vibrant colors of a rainbow. The beauty of this force lies in its dual nature. It can both attract and repel, shaping the relationships between particles and the materials they create. The weak force, though less familiar, is equally important. It governs the processes of radioactive decay, a phenomenon that has profound implications for the stability of atoms and the energy produced by stars. Imagine the immense power contained within a single atom, the potential for transformation, as particles shift and change under the influence of this force. Gravity, the force that pulls us to the ground and governs the motion of celestial bodies, is perhaps the most familiar yet enigmatic force of all. While it is significantly weaker than the others at the subatomic level, its reach is vast, affecting everything from the smallest particles to the grandest galaxies. Every object with mass exerts a gravitational pull, binding the universe together in a delicate dance of attraction. Understanding these forces is essential for appreciating the intricate web of interactions that govern the universe. The study of subatomic particles and the forces that act upon them is a cornerstone of physics, shedding light on the fundamental principles that dictate the behavior of matter. As noted by a prominent physicist, physics is like sex. Sure, it may give some practical results, but that's not why we do it. This sentiment captures the essence of scientific inquiry, a pursuit driven by curiosity and wonder. The field of particle physics seeks to unravel the mysteries of the subatomic world. Its goals extend beyond mere classification. Scientists aim to discover the underlying truths of the universe, to probe the very fabric of reality. This journey is not just an academic endeavor. It is a quest for knowledge that has profound implications for our understanding of existence itself. In laboratories around the globe, physicists are engaged in groundbreaking research, utilizing powerful particle accelerators to smash particles together at incredible speeds. These collisions create conditions akin to those present just moments after the Big Bang, allowing scientists to observe the behavior of particles and the forces that govern them. The data collected from these experiments is a treasure trove of insights, revealing the fundamental laws that shape our universe. Imagine standing in the presence of an accelerator, witnessing particles racing through the tunnels, propelled by immense energies. The excitement in the air is palpable as researchers await the results of their experiments, their hearts racing in tandem with the particles they study. Each discovery is a piece of a larger puzzle, bringing us closer to understanding the very nature of reality. As we continue to explore the subatomic realm, we encounter the standard model of particle physics, a framework that categorizes all known fundamental particles and forces. This model elegantly describes how particles interact through three of the four fundamental forces: the electromagnetic, weak, and strong forces. While gravity remains outside this framework, the quest to unify these forces continues to inspire physicists, who dream of a comprehensive theory that encapsulates all aspects of the universe. The Standard Model is not just a collection of particles. It is a detailed map of the interactions that define our reality. At its core lie quarks and leptons, the building blocks of matter, and force carriers known as gauge bosons, which mediate the fundamental forces. The Higgs boson, discovered in recent years, adds another layer to this intricate structure, providing insight into how particles acquire mass. As we ponder these discoveries, we are reminded of the words of a visionary physicist. The great physicists of the past laid the foundation, and now it is our turn to build upon it. This legacy of scientific inquiry fuels the passion of today's researchers, who stand on the shoulders of giants as they delve into the unknown. The study of subatomic particles is not merely an academic pursuit. It has far-reaching implications for our everyday lives. The technologies that emerge from this research, such as medical imaging techniques and advancements in materials science, have transformed how we understand and interact with the world. Consider the role of particle physics in medicine. Techniques such as positron emission tomography or PET scans rely on the principles of particle physics to visualize the inner workings of the human body. By detecting the gamma rays emitted during radioactive decay, doctors can identify diseases at their earliest stages, offering a glimpse into the potential for healing. Furthermore, advancements in our understanding of particle interactions have led to innovations in materials science, enabling the development of new materials with extraordinary properties. From superconductors that carry electricity without resistance to nanomaterials that can revolutionize technology, the influence of particle physics permeates every facet of modern life. As we reflect on the significance of studying subatomic particles and forces, we recognize that this journey is not just about answering questions, but also about igniting curiosity and wonder. The universe is a vast and intricate puzzle, filled with mysteries waiting to be uncovered. Every discovery leads to new questions, inviting us to explore further and deeper. What lies beyond the current understanding? What new particles or forces await our discovery? The quest for knowledge is a continuous thread, weaving together generations of scientists who have dared to ask the profound questions that shape our understanding of existence. In this vast pursuit, we find solace and inspiration. The calm beauty of the universe, from the tiniest particles to the grandest galaxies, invites us to marvel at the interconnectedness of all things. Each atom, each particle, sings its own song in the grand symphony of existence, reminding us of the intricate design of the cosmos. As we embark on this journey through the subatomic landscape, let us carry with us the spirit of inquiry, the desire to explore the unknown, and the wonder that accompanies every new discovery. The world of subatomic particles and forces awaits, ready to reveal its secrets to those who dare to seek. As we immerse ourselves further into the world of particle physics, we encounter the intriguing concept of antimatter. Imagine a mirror image of the matter that surrounds us, where every particle has a corresponding antiparticle. For instance, the antiparticle of an electron is called a positron, which possesses a positive charge. When a particle and its antiparticle meet, they annihilate each other in a burst of energy, exemplifying the profound relationship between matter and energy as articulated by the famous equation from Einstein. The existence of antimatter raises questions that challenge our understanding of the universe. Why is it that the universe is primarily composed of matter, while antimatter appears to be so scarce? Some scientists speculate that, during the Big Bang, a slight imbalance in the production of matter and antimatter may have led to the predominance of the former. This mystery continues to intrigue physicists, prompting experiments to explore the properties of antimatter and its implications for our understanding of cosmic evolution. Not far from this contemplation lies the realm of neutrinos, often referred to as the ghosts of the subatomic world. These incredibly light and neutral particles travel through matter as if it were invisible, interacting only through the weak force. Their elusive nature means that trillions of neutrinos pass through our bodies every second without us even noticing. Yet, despite their invisibility, neutrinos hold vital information about the processes occurring within stars and the very fabric of the universe. Renowned physicist Wolfgang Pauli once remarked, "In the light of the current state of knowledge, one must admit that neutrinos are the least understood particles." This statement underscores the ongoing quest to comprehend these enigmatic particles, which may hold clues to unanswered questions about the universe's fundamental workings. Could neutrinos illuminate the mysteries of dark matter, the unseen substance that makes up a significant portion of the universe? Their study is an active area of research, highlighting the endless possibilities that await within the subatomic realm. As we draw our attention to the interplay of forces within particle physics, it is essential to recognize the role of the Higgs field. This invisible field permeates the universe, giving mass to particles as they interact with it. The discovery of the Higgs boson in recent years was a monumental achievement, validating a crucial piece of the Standard Model. Visualize a particle moving through a field of molasses. As it encounters resistance, it gains mass. This analogy beautifully captures the essence of how particles acquire their mass through interactions with the Higgs field. The implications of the Higgs mechanism extend far beyond theoretical physics. The understanding of mass and its origins informs many aspects of our daily lives, from the stability of atoms to the synthesis of complex molecules. As we ponder the significance of this discovery, we are reminded of how interconnected our physical reality is, shaped by the subtle dance of particles and fields. As we traverse this landscape of subatomic particles and forces, we cannot overlook the contributions of outstanding individuals who have shaped our understanding. Figures like Marie Curie, who pioneered research on radioactivity, and Richard Feynman, known for his work on quantum electrodynamics, have left indelible marks on the field. Their passion for discovery and insatiable curiosity exemplify the spirit of scientific inquiry. Feynman once stated, "The pleasure of finding things out is one of the most incredible sources of enjoyment in my life." These luminaries inspire a new generation of physicists, encouraging them to embrace the unknown and pursue the questions that ignite their curiosity. The field of particle physics is not static. It is a vibrant and evolving discipline, constantly pushing the boundaries of what we know. As new technologies and methodologies emerge, the potential for groundbreaking discoveries continues to expand. As we reflect on the importance of studying subatomic particles and the forces that govern them, we recognize that this pursuit is not merely academic. It is a journey of exploration that intertwines with the very essence of existence. Each particle, each force, contributes to the grand narrative of the universe, shaping the cosmos in ways we are only beginning to comprehend. The study of these fundamental elements has far-reaching consequences, influencing areas such as energy production, environmental sustainability, and even our understanding of the origins of the universe itself. The potential applications of particle physics are vast, from advancements in renewable energy technologies to insights into the fundamental nature of time and space. As we immerse ourselves in this intricate world, let us remain open to the wonders that lie ahead. The quest for knowledge is an infinite journey, filled with twists and turns, challenges and triumphs. Each question answered begets new inquiries, propelling us toward deeper understanding. Wouldn't it be remarkable to think that the answers we seek might not only reshape our understanding of the universe, but also our place within it? In this exploration, let us embrace the beauty of discovery. The universe, with its intricate tapestry of particles and forces, invites us to ponder our existence, to seek connections between the known and the unknown, and to revel in the joy of understanding. As we continue to delve into the mysteries of subatomic particles, we carry with us the spirit of curiosity, ready to uncover the secrets that await in the vast expanse of the cosmos. Chapter 2: The Role of Particle Colliders in Research. Particle colliders stand as monumental achievements in our quest to understand the universe at its most fundamental level. These extraordinary machines are not merely constructs of metal and wires. They are intricate designs purposefully built to unlock the secrets hidden within the subatomic realm. Their primary purpose is to accelerate particles to astonishing speeds, often approaching that of light itself, allowing scientists to probe deeper into the fabric of matter. Imagine a vast circular tunnel, stretching for miles, encased in a cavernous facility. This is the layout of a particle collider, where particles are propelled in opposing directions at remarkable velocities. In the case of the Large Hadron Collider, located near Geneva, Switzerland, protons are pushed to nearly the speed of light through the use of advanced electromagnetic fields. These fields guide the particles along the collider's path, creating an environment where collisions can occur at staggering energy levels. As these particles race around the collider, they gather momentum, their energies increasing with each revolution. It is a mesmerizing sight to consider. Tiny particles, the very essence of what makes up our universe, spiraling at incomprehensible speeds within a colossal underground ring. The purpose behind this acceleration is not simply to achieve speed for its own sake. It is about creating conditions that mirror those just moments after the Big Bang, when our universe began to take shape. The collisions that take place within these colliders are crucial. When particles collide at such high energies, they do not just bounce off each other. They can break apart, revealing their constituent parts and producing entirely new particles. This process is akin to peeling back the layers of an onion, exposing the fundamental components that make up the universe. As physicist Michio Kaku once expressed, the universe is a symphony of vibrating strings, suggesting that at the core of matter lies a complex interplay of forces and particles, each contributing to the grand design of existence. Now, let us take a moment to envision the significance of these collisions. Each event is a fleeting moment in time, yet it holds the potential to unveil properties of particles that have remained elusive for centuries. The data collected from these collisions is akin to a treasure trove of information, allowing scientists to test theories and confirm hypotheses about the fundamental forces and particles that govern our universe. Among the most notable of these colliders is the Large Hadron Collider, which has made headlines around the world for its groundbreaking discoveries. It was here that, in the summer of 2012, physicists announced the discovery of the Higgs boson, a particle that had been theorized for decades but remained undiscovered until that pivotal moment. The Higgs boson is often referred to as the God particle because it plays a crucial role in imparting mass to other particles, a concept central to our understanding of how matter is formed. Moreover, the Large Hadron Collider is not alone in this endeavor. Other significant colliders, such as the Fermilab Tevatron and Japan's Super KEKB, have also contributed to the field of particle physics. Each collider has its unique design and purpose, yet they all share a common goal: to explore the unknown and push the boundaries of our understanding. Consider the implications of these findings. Each collision provides a snapshot of the universe's early moments, a glimpse into the forces that shaped everything from galaxies to stars to the very atoms in our bodies. As we learn more about these particles, we also gain insights into the fundamental forces of nature, including electromagnetism and the strong and weak nuclear forces. The role of particle colliders in research is not merely academic. It sets the stage for profound discoveries that can alter our understanding of reality. Imagine a world where the fundamental laws of physics could be rewritten, where the very nature of existence might shift based on new evidence gathered from these collisions. The potential for breakthroughs is limitless, and the journey towards understanding is ongoing. As we reflect on the scientists who dedicate their lives to this pursuit, we find inspiring figures like Fabiola Giannotti, the first female director of CERN. Her contributions to the field exemplify the spirit of curiosity and determination that drives particle physics forward. Giannotti has said, "Science is not just about finding new things, it is also about challenging established ideas." Her words resonate deeply within the halls of research facilities, where each experiment is an opportunity to challenge the known and explore the unknown. In this world of particle colliders, we are constantly reminded of the delicate balance between discovery and understanding. The collisions may be brief, but their consequences echo throughout the scientific community and beyond. With every burst of energy and every emerging particle, we are invited to ponder the larger questions of existence. What is the nature of reality? How did the universe come to be? What mysteries remain hidden, waiting to be uncovered? The significance of particle collisions extends beyond mere academic interest. It touches the very essence of who we are and our place within the cosmos. These experiments serve as a reminder that the universe is not static. It is a dynamic, ever-evolving entity, shaped by the forces and particles we are just beginning to comprehend. As we continue to explore the role of particle colliders in research, we unveil a world filled with promise and possibility. The journey ahead is illuminated by the flickering lights of discovery, beckoning us to join in the quest for understanding. With each collision, we are drawn closer to the heart of the universe, uncovering the secrets that lie beneath the surface of matter and revealing the interconnectedness of all things. The process of colliding particles at such extraordinary energies allows scientists to probe not only the individual characteristics of these particles, but also the interactions that govern their behavior. Each collision serves as a cosmic experiment, providing insights into the fundamental forces that orchestrate the universe. Imagine, if you will, a grand symphony where every particle plays a note, contributing to a harmonious understanding of existence itself. When particles collide, the results can be both astonishing and perplexing. As energy transforms into mass, new particles can emerge, some of which might exist only for an infinitesimal fraction of a second before decaying into more familiar forms. This fleeting nature mirrors the ephemeral beauty of a fireworks explosion, bursting into a cascade of colors before fading into the night sky. The particles produced in these collisions can be rare and exotic, challenging our understanding of the fabric of reality. For instance, the discovery of heavy quarks, such as the top quark, has provided profound insights into the standard model of particle physics, the framework that describes how particles and forces interact. The top quark is the heaviest of all observed quarks, a testament to the complexities of mass and energy. It was first discovered at Fermilab's Tevatron Collider, a pivotal moment in the quest to unravel the mysteries of matter. The existence of such heavy particles raises questions about the symmetry and structure of the universe, inviting scientists to explore theories beyond the standard model. In addition to unveiling new particles, collisions offer a glimpse into phenomena that occur under extreme conditions, akin to those present in the early universe. The temperatures and energies achieved in colliders like the Large Hadron Collider create an environment where quarks and gluons, the fundamental constituents of protons and neutrons, can exist freely. This state, known as quark-gluon plasma, represents a primordial phase of matter, a fleeting echo of the conditions that prevailed just moments after the Big Bang. Scientists can study this exotic plasma to uncover the nature of the strong force, which binds quarks together inside protons and neutrons. As we ponder the implications of such discoveries, we are reminded of the words of physicist Richard Feynman, who said, "The most important thing is not to stop questioning." Each collision ignites a spark of curiosity, prompting scientists to delve deeper into the unknown. What do these newly discovered particles tell us about the fundamental nature of reality? How do they fit into the grand puzzle of the universe, bridging the gaps in our understanding? The data generated from these collisions is vast and complex, resembling a labyrinth of information that scientists must decipher. Advanced detectors, equipped with sophisticated technology, capture the remnants of each collision, meticulously recording the paths and energies of the particles produced. This information is then analyzed using powerful computational methods, transforming raw data into meaningful insights about the universe's workings. The collaborative efforts of scientists from diverse backgrounds foster an environment ripe for innovation, as they share knowledge and techniques to unravel the intricate threads of particle physics. Among the myriad of discoveries made possible by colliders, the search for dark matter stands out as a captivating pursuit. Dark matter, which constitutes a significant portion of the universe's mass, remains elusive and mysterious. It does not emit light or interact with electromagnetic forces, making it invisible to conventional detection methods. However, its presence is inferred from gravitational effects on galaxies and cosmic structures. Colliders are instrumental in the search for potential candidates for dark matter, such as weakly interacting massive particles or WIMPs. If discovered, these particles could revolutionize our understanding of the universe, shedding light on one of its greatest mysteries. The significance of particle collisions extends beyond theoretical considerations. They also have practical applications that ripple through various fields of science and technology. The advancements in detector technology and computational techniques developed for particle colliders have influenced medical imaging, cancer treatment, and materials science. For example, particle therapy, a cutting-edge cancer treatment method, utilizes charged particles to target tumors with precision, minimizing damage to surrounding healthy tissue. As we explore the realm of particle physics, we encounter brilliant minds who have shaped the field. One such figure is Maria Goeppert-Mayer, who, alongside J. Hans D. Jensen and Edwin Macmillan, was awarded the Nobel Prize in Physics for her work on the nuclear shell model. Mayer's contributions exemplify how the pursuit of knowledge transcends gender and societal boundaries, inspiring future generations of scientists to explore the mysteries of the universe. Imagine a world where the discoveries made in particle colliders lead to breakthroughs that transform our understanding of energy, matter, and the very fabric of reality. What if we could harness the principles of particle physics to develop new energy sources or create materials with unprecedented properties? The potential for innovation is boundless, inviting us to dream of a future shaped by the insights gleaned from these powerful machines. As we continue to unravel the complexities of particle collisions, we are reminded that the journey of discovery is as significant as the discoveries themselves. Each step forward brings us closer to understanding our universe, its origins, and its ultimate fate. The collisions within these colliders are not merely events, they are windows into the very essence of existence, urging us to explore the questions that define our place in the cosmos. With every experiment, we are invited to reflect on the nature of knowledge and the relentless pursuit of truth. The mysteries of the universe await, and through the lens of particle colliders, we are one step closer to illuminating the dark corners of our understanding. Each collision is a reminder that the universe is a vast, interconnected web of phenomena, with secrets waiting to be unveiled, urging us to remain curious and open to the wonders that lie ahead. Chapter 3: The Mechanics of Particle Acceleration. Envision a grand arena, an expansive underground labyrinth where the very essence of matter is put to the test. This is the realm of particle colliders, where the art of accelerating particles unfolds. Here, particles are not merely pushed, they are propelled to extraordinary speeds, their kinetic energy transformed into a powerful tool for discovery. The process begins with the careful injection of particles into the accelerator. These particles, often protons or electrons, are gathered and prepared, akin to athletes warming up before a race. They are cooled and aligned, ensuring they are ready to embark on their journey through the intricate machinery. Once injected, the particles are accelerated using electromagnetic fields. These fields act like invisible hands, guiding the particles along their designated paths. Imagine a sleek stream of water flowing through a garden hose. The electromagnetic fields compress and focus the particles, increasing their velocity as they journey through the accelerator. The energy imparted to them is immense, allowing them to reach speeds that are a significant fraction of the speed of light. This acceleration is not a simple task. It requires a delicate balance of precision and power. Particle accelerators can be broadly categorized into two types: linear and circular. Linear accelerators propel particles in a straight line, allowing them to gain speed as they travel through a series of accelerating structures. Picture a winding road that gently inclines, giving vehicles the opportunity to gather momentum as they ascend. In contrast, circular accelerators, like the Large Hadron Collider, use a different approach. They guide particles in a circular path, allowing them to spiral around multiple times, gaining energy with each revolution. This method is akin to a carousel, where each spin adds a little more speed, building up to a thrilling climax. The energy levels achieved in modern colliders are nothing short of breathtaking. As particles circle around the collider, they accumulate energy at an astonishing rate. When two particles collide, the energy released can be converted into mass, giving rise to new particles. This phenomenon is elegantly described by Einstein's famous equation, which illustrates the relationship between energy and mass. Imagine a cosmic dance, where energy transforms into matter, revealing the hidden layers of the universe. The discoveries made in these collisions have reshaped our understanding of fundamental physics, unveiling secrets that lay dormant since the dawn of time. Yet this journey through the realm of particle physics is not without its challenges. Accelerating particles to such high speeds involves overcoming significant obstacles. The electromagnetic fields used to steer and accelerate the particles must be finely tuned and maintained. Any fluctuation can result in a loss of momentum or even a catastrophic failure. Scientists work tirelessly to ensure that these systems operate with unparalleled precision, constantly monitoring the conditions within the accelerator. Another challenge lies in the sheer scale of the colliders themselves. The Large Hadron Collider, for instance, stretches over 17 miles in circumference. The engineering required to construct such a colossal instrument demands not only ingenuity, but also collaboration across various scientific disciplines. It is a testament to human perseverance and creativity, a structure that embodies the relentless pursuit of knowledge. Furthermore, as particles collide at unprecedented energies, they generate vast amounts of data. The detectors surrounding the collision points capture this data, recording every event with meticulous detail. However, sifting through this information is akin to finding a needle in a haystack. Scientists employ sophisticated algorithms and computational methods to analyze the results, seeking patterns and anomalies that could lead to groundbreaking discoveries. As we ponder these complexities, we might wonder, what motivates the scientists who dedicate their lives to this work? Many of them feel a profound sense of purpose, driven by a desire to unravel the mysteries of the universe. As one physicist expressed, we are not just searching for answers, we are exploring the very fabric of existence. This quest for understanding fuels their passion, propelling them through the challenges they face. The mechanics of particle acceleration, while intricate, reveal a world of possibilities. Each particle accelerated, each collision observed, is a step closer to comprehension. In this grand experiment, the universe invites us to explore its depths, to question the nature of reality itself. The boundaries of our knowledge expand with every discovery, illuminating the path ahead. In this journey through the mechanics of particle acceleration, one cannot help but marvel at the interconnectedness of all things. The particles we study, the forces we manipulate, and the energy we harness are all part of a larger narrative, the story of our universe. It is a story rich with wonder and complexity, a tale that beckons us to listen closely, to ponder deeply, and to embrace the unknown. As we stand on the precipice of discovery, we are reminded of the beauty inherent in the pursuit of knowledge. The challenges that lie ahead serve not to deter us, but to inspire us. In the realm of particle physics, every question asked is an invitation to explore, every challenge faced is an opportunity for growth. The journey continues, and with it, the promise of revelations yet to come. As we immerse ourselves in the intricate world of particle acceleration, we begin to appreciate the sheer scale of energy involved. The energies generated in modern colliders are staggering. Consider the vast amount of kinetic energy required to propel particles close to the speed of light. The Large Hadron Collider, for instance, achieves energy levels that allow particles to collide with energies equivalent to the mass of a small car, all concentrated into a minuscule point. This intensity is not merely for show, it serves a purpose. In these moments of collision, when particles collide with such force, we can witness phenomena that have not occurred since the infancy of the universe itself. Imagine the moments just after the Big Bang, a time when the universe was a hot, dense soup of particles. The collisions in particle colliders recreate these primordial conditions, allowing scientists to study the fundamental forces and particles that shaped the cosmos. Each collision produces a variety of particles, some of which are fleeting, existing only for a fraction of a second before disappearing into the void. This transient nature of particles is reminiscent of a fleeting dream, where something profound and beautiful is experienced but can never be fully grasped. The intricacies of these processes invite us to ponder. How do scientists measure and interpret these ephemeral events? At the heart of this endeavor are sophisticated detectors designed to capture the myriad particles created in each collision. These detectors are marvels of engineering, composed of layers of different materials that serve various purposes, from tracking the paths of charged particles to measuring their energy. When a collision occurs, these detectors spring to life, recording the resulting particles with remarkable precision. The data they generate is akin to a symphony, where each note reveals a piece of the greater narrative of the universe. However, the journey of particle acceleration is not without its hurdles. One of the foremost challenges scientists face is the phenomenon known as synchrotron radiation, particularly in circular accelerators. As charged particles travel along curved paths, they emit energy in the form of light, which can lead to energy loss. This loss is detrimental, as it requires additional energy input to maintain the particle's speeds. Imagine a bicycle racing uphill. If the rider begins to lose momentum, they must exert even more effort to keep moving forward. In the context of particle colliders, this energy loss necessitates constant vigilance from researchers who must adjust the systems to compensate for these emissions, ensuring that the particles maintain their high velocities. Moreover, the management of heat generated during acceleration poses another significant challenge. The immense energies involved can lead to substantial temperature increases within the accelerator's components. A delicate balance must be maintained to prevent overheating, which could compromise the integrity of the machine. Cooling systems, often likened to the intricate networks of veins in a living organism, circulate coolant to dissipate excess heat, ensuring that the accelerator remains operational and efficient. The engineering feats involved in constructing and maintaining these colossal machines are nothing short of extraordinary. The collaboration required spans continents and disciplines, uniting physicists, engineers, and computer scientists under a common goal. Each component, from the magnets that steer the particles to the electronics that control the systems, is meticulously designed and tested. The Large Hadron Collider, for example, comprises thousands of magnets, each precisely aligned to create the perfect path for the particles. The synchronization of these components is akin to a carefully orchestrated performance, where each musician plays their part in harmony to create a beautiful symphony of discovery. As we reflect on these monumental efforts, we might ask ourselves, what drives this relentless pursuit of knowledge within the scientific community? The answer lies in the profound curiosity that fuels exploration. Scientists are motivated by the desire to answer fundamental questions about the universe, questions that have perplexed humanity for centuries. The quest to understand the nature of dark matter and dark energy, for instance, leads researchers to continue refining their methodologies and seeking new avenues of investigation. The work of pioneers in the field serves as a testament to this unyielding spirit. Figures such as Robert Wilson, who played a pivotal role in the development of the Fermilab accelerator, once stated, "The greatest gift of science is that it enables us to see the world as it is." This perspective inspires countless scientists to push the boundaries of what we know, embarking on journeys that lead to astonishing discoveries and groundbreaking insights. In this dance of particles and energies, we discover not just the mechanics of the universe, but also the essence of human inquiry. The challenges faced in particle acceleration serve to enhance our understanding, illuminating the paths we must traverse in our quest for knowledge. Each setback is met with resilience, and each challenge becomes an opportunity for growth. As we continue exploring the mechanics of particle acceleration, let us marvel at the interconnectedness of every effort, every particle, and every discovery. It is a journey that transcends the confines of science, inviting us to consider our place within the vast cosmos. Each experiment, each collision, is a testament to the human spirit's insatiable curiosity, delivering us closer to understanding the mysteries that lie beyond the veil of our current knowledge. In this pursuit, we find not only the mechanics of the universe, but also our own capacity for wonder and exploration. As particles whirl through the intricate pathways of the collider, they not only gain speed, but also experience a transformation that raises profound questions about the very nature of existence. Each collision is more than just a meeting of particles. It is a moment when the fabric of reality is tested, revealing layers of complexity that have long remained hidden. Imagine, for a moment, the thrill of witnessing the birth of particles that have not existed since the early moments of the universe, new forms of matter emerging from the chaos of energy. This is the allure of high-energy physics, where every experiment brings us closer to understanding the fundamental forces that govern our universe. In the throes of particle collisions, scientists are faced with the task of interpreting the aftermath. The collisions create an array of particles, and each one carries its own story, its own implications. The data produced is staggering, a cacophony of information that must be meticulously analyzed. To do this, scientists rely on advanced computational techniques, capable of sifting through mountains of data in search of meaningful patterns. Imagine a vast library, where each book represents a potential discovery, and the researchers are the librarians, tasked with uncovering the truths that lie within. The challenge of data analysis is compounded by the ephemeral nature of many of the particles produced in collisions. Some exist for mere fractions of a second, vanishing before they can be observed directly. This fleeting existence is reminiscent of fireflies on a summer night, beautiful but elusive. Yet, scientists have developed ingenious methods to indirectly detect these particles, using their decay products as clues to piece together the puzzle. It is a delicate art, one that requires both patience and creativity, as researchers strive to understand the implications of what they observe. Furthermore, the implications of particle acceleration extend beyond the realm of basic physics. The technologies developed for colliders have found applications in various fields, from medicine to materials science. For instance, the techniques used in particle imaging have revolutionized medical imaging, allowing for earlier detection of conditions such as cancer. As we consider these advancements, we might ask ourselves, how does the pursuit of knowledge in one field illuminate others? The interconnectedness of scientific inquiry becomes apparent as discoveries in particle physics ripple through different domains, fostering innovation and progress. As we reflect on the challenges and triumphs of particle acceleration, we can draw inspiration from the figures who have shaped this field. Scientists like Enrico Fermi, who pioneered the first nuclear reactor, remind us of the power of curiosity and determination. Fermi once said, "The physicist's greatest tool is his imagination." This sentiment resonates deeply within the community, as researchers continue to push the boundaries of what is possible, driven by a desire to explore the uncharted territories of knowledge. In this ongoing journey, we find a sense of calm amidst the complexities. The persistent quest for understanding fosters a profound connection to the universe, inviting us to contemplate our place within it. Imagine standing amidst the vast cosmos, where each star represents a question waiting to be answered, each galaxy a story yearning to be told. The mechanics of particle acceleration serve as a bridge, guiding us toward these revelations while reminding us of the beauty inherent in the pursuit itself. As we delve further into the mechanics of particle acceleration, the interplay between energy and matter takes center stage. The collisions not only create new particles, but also provide insights into the fundamental forces that hold the universe together. The strong force, for instance, binds protons and neutrons within atomic nuclei, while the weak force governs processes such as radioactive decay. Understanding these forces is akin to deciphering the language of the cosmos, allowing us to connect the dots in the grand narrative of existence. In this intricate dance of particles, we are reminded that every discovery, every breakthrough, every setback contributes to the larger picture. The challenges faced in the acceleration process are not roadblocks, but rather stepping stones on the path to enlightenment. Each experiment is a testament to human resilience, a reflection of our unwavering commitment to understanding the universe's mysteries. As the chapter unfolds, the journey through particle acceleration invites us to remain open to the wonders that lie ahead. Each collision, each experiment, and each analysis is a note in the symphony of science, harmonizing to reveal the profound truths of our existence. And in the quiet moments of contemplation, we find solace in the knowledge that the pursuit of understanding is a journey without end, forever illuminating the path before us. Chapter 4: Collision Events: What Happens in the Lab. In the heart of the collider, where science meets spectacle, collision events emerge as the defining moments of particle physics research. Imagine the instant when two protons, racing toward each other at speeds that defy comprehension, finally collide. This moment, a fleeting flash in the grand timeline of the universe, is where new particles can emerge, echoing the violent beginnings of the cosmos. As these protons smash together, they create conditions reminiscent of the moments just after the Big Bang, a primordial dance of energy and matter. The collision itself is a chaotic yet beautifully orchestrated event, giving birth to a cascade of subatomic particles. When protons collide, they don't merely bounce off one another. They disintegrate into their constituent parts, producing a shower of particles that can include quarks, gluons, and even exotic particles like the Higgs boson. These fleeting entities exist for mere fractions of a second, but their presence is critical. They bear messages about the fundamental forces that govern our universe, whispering secrets that scientists strive to decode. To capture these ephemeral moments, detectors play a vital role. Picture a sprawling array of sophisticated instruments, each designed to observe different aspects of these collision events. Detectors come in various shapes and sizes, from large, cylindrical structures to intricate layers of sensors designed to track the paths of charged particles. At the Large Hadron Collider, for instance, the ATLAS and CMS detectors are marvels of engineering, capable of capturing the immense data produced by countless collisions. These detectors utilize a combination of technologies, including electromagnetic calorimeters and tracking systems, to identify the particles emerging from collisions. As particles pass through the detector, they leave behind a trail of signals, much like footprints in the sand. The detectors measure these signals, translating them into data that scientists can analyze. The information gathered is brilliant and complex, revealing the energies, momenta, and types of particles produced in each event. But how do researchers sift through the vast amounts of data generated by these collisions? This is where the role of data analysis becomes paramount. Each collision event produces an overwhelming amount of information, and scientists must determine which events hold significance for their research. This is where the concept of triggers comes into play. Imagine a gatekeeper standing at the threshold of discovery, deciding which collision events warrant further investigation. Triggers are sophisticated algorithms that sift through the data in real time, selecting events based on predefined criteria. They act as filters, ensuring that only the most interesting collisions are recorded for further study. For example, if a collision produces a particle with characteristics consistent with the Higgs boson, the trigger will flag this event for detailed analysis. The elegance of this system lies in its ability to prioritize significant data while discarding the mundane, allowing researchers to focus their attention on the most promising leads. The analysis of collision events is a meticulous process that blends creativity with rigorous scientific methodology. Once significant events have been identified, scientists delve into the data, employing advanced statistical techniques and computational tools to uncover patterns and correlations. They examine the properties of the particles produced, their energies, and how they interact with one another. One of the most intriguing aspects of this analysis is the search for rare events. The Higgs boson, for instance, was discovered through the analysis of a minuscule fraction of collision events that matched the expected signature of this elusive particle. This search requires patience and perseverance, as researchers often comb through mountains of data, driven by the possibility of uncovering something extraordinary. Throughout this process, the collaborative spirit of the scientific community shines. Physicists and engineers from around the world come together, sharing insights and expertise to tackle the challenges posed by data analysis. This collaboration is reminiscent of an intricate dance, where each participant plays a vital role in the pursuit of knowledge. As one physicist eloquently stated, "Science is the poetry of reality." In this quest for understanding, the collision events serve as a reminder of the interconnectedness of all things. Each interaction within the collider mirrors the larger interactions of the cosmos, where particles collide, merge, and transform, creating the universe as we know it. The insights gained from these collisions extend beyond the realm of particle physics. They influence our understanding of the very fabric of reality. As we explore the outcomes of these collision events, it becomes evident that they are not just scientific curiosities, but keys to unlocking the mysteries of existence itself. What is the nature of dark matter? How do fundamental forces interact? These questions resonate through the halls of research laboratories, driving scientists to push the boundaries of what we know. So, let us take a moment to imagine the profound implications of these collisions. Each event is a story waiting to be told, a piece of the puzzle that contributes to our understanding of the universe. As particles collide and interact, they create a symphony of possibilities, offering glimpses into realms that lie beyond our current grasp. In the world of particle colliders, every collision is a moment of potential discovery, a fleeting opportunity to witness the unseen. The detectors capture the echoes of these events, allowing us to glimpse the intricate workings of nature at its most fundamental level. Through careful analysis and collaboration, researchers endeavor to piece together the narrative of our universe, one collision at a time. The journey through collision events is not merely a scientific pursuit. It reflects humanity's insatiable curiosity and desire to understand our place in the cosmos. As we continue to explore these interactions, we are reminded of the beauty that lies within the complexity of nature. Each collision carries with it the promise of enlightenment, a step closer to understanding the grand tapestry of existence. In the end, the lab becomes a sanctuary of discovery, where the collision of particles mirrors the collision of ideas and aspirations. It is here, in this sacred space, that scientists work tirelessly to unravel the mysteries of the universe, driven by a passion for knowledge and the belief that every collision event holds the potential to change our understanding of reality forever. As the data from collision events flows in, the tapestry of information becomes almost poetic in its complexity. Each recorded event is layered with significance, beckoning scientists to explore its depths. The analysis of these events is not merely a mechanical process. It is an art that requires an intuitive understanding of the underlying physics. Researchers must hone their skills in discerning patterns amidst chaos, often drawing upon their creativity to generate new hypotheses. Imagine a vast ocean of data, where each wave represents a collision event, crashing against the shores of understanding. Within this ocean, scientists seek islands of knowledge, each one a rare discovery that adds to the collective understanding of the universe. The challenge lies in identifying these islands before they slip away into the depths of noise and irrelevance. To achieve this, scientists employ a variety of advanced tools and techniques. One remarkable approach is the use of machine learning algorithms, which can analyze vast datasets with an efficiency that surpasses human capability. These algorithms are trained to recognize patterns that might not be immediately evident, allowing researchers to uncover hidden correlations that can lead to groundbreaking discoveries. Imagine a digital companion, tirelessly sifting through mountains of data, illuminating paths that might have remained obscured to the naked eye. With each successful analysis, we find ourselves on the brink of understanding phenomena that once seemed unattainable. The potential for discovering new particles or confirming theoretical predictions fuels the excitement of researchers. For instance, the discovery of the Higgs boson at the Large Hadron Collider was a triumphant moment in the scientific community, marking the culmination of years of collaborative effort and intricate analysis. The excitement surrounding this event was palpable, as scientists celebrated a monumental step in validating the standard model of particle physics. Yet, not all discoveries come easily. The search for new particles often resembles a treasure hunt, where the prize is shrouded in uncertainty. Rare events, such as those predicted by theories beyond the standard model, are often elusive and require an extraordinary amount of data to unearth. Scientists must remain patient and vigilant, as each collision holds the potential for a breakthrough that could reshape our understanding of reality. As the data is meticulously analyzed, the role of triggers becomes increasingly vital. These triggers act as the first line of defense, swiftly filtering through the flood of events to identify those worthy of further examination. Imagine a vigilant guard, standing at the gates of knowledge, ensuring that only the most promising collision events are allowed to pass into the realm of detailed scrutiny. Triggers operate based on predefined conditions, designed to capture specific characteristics that might indicate the presence of new physics. For example, if a collision yields a particle with an unusual mass or decays in a manner that defies conventional expectations, the trigger will flag it for further analysis. This system ensures that scientists can focus their efforts on the most intriguing phenomena, allowing them to maximize their chances of uncovering something truly extraordinary. As we reflect on the role of triggers, we are reminded of the delicate balance between exploration and efficiency in scientific research. How can one prioritize the unknown while ensuring that significant findings do not slip through the cracks? This question drives researchers to continually refine their methods, to innovate in ways that enhance their ability to discern the remarkable within the mundane. The process of analyzing collision events, then, emerges as a dance between discovery and discernment. Each step forward requires an intricate choreography of technology, intuition, and collaboration. The interplay of human insight and computational power creates an environment ripe for breakthroughs, where serendipity can intertwine with careful planning. As we delve deeper into the mechanics of detection and analysis, the role of collaboration becomes increasingly apparent. The pursuit of understanding in particle physics is not a solitary endeavor. It is a collective journey undertaken by a global community of scientists. Researchers from diverse backgrounds come together to share their expertise, insights, and aspirations, united by a common goal: to unravel the mysteries of the universe. Consider the sheer scale of collaboration at institutions like CERN, where thousands of scientists, engineers, and technicians work side by side. Each individual contributes a unique skill set, enhancing the overall capability of the research community. This spirit of cooperation fosters an atmosphere of innovation, where ideas can flourish and be challenged in a supportive environment. In this vibrant ecosystem, the collision events themselves serve as catalysts for discussion and inspiration. Researchers gather around data sets, sharing interpretations and brainstorming new avenues for exploration. The energy in these discussions is palpable, igniting a sense of purpose that drives the pursuit of knowledge. As we journey through the intricate landscape of collision events, we are reminded that science is as much about the process as it is about the discoveries. The thrill of exploration, the joy of collaboration, and the anticipation of revelation create a rich tapestry of experiences that define the scientific journey. Each collision event becomes a thread in this tapestry, contributing to a greater understanding of the universe and our place within it. In this environment of inquiry, every question leads to another. What new insights will emerge from the next collision? What hidden realms of existence remain to be explored? The answers to these questions lie within the data, waiting patiently to be unveiled. The pursuit of knowledge is an endless journey, one that beckons us to keep pushing the boundaries of our understanding. As the data continues to flow, the collision events remind us that the universe is alive with possibility, offering glimpses of the extraordinary for those willing to seek them out. With each moment of discovery, we draw closer to unraveling the intricate connections that bind us to the cosmos, illuminating the beauty that lies within the heart of existence. Chapter 5: Discovering New Particles Through Collisions. The world of particle physics is an adventurous realm, where the tiniest collisions can lead to groundbreaking discoveries. Imagine, if you will, two protons hurtling through a vast underground tunnel, each racing towards the other at nearly the speed of light. As they approach one another, their energies converge, and in a split second, they collide with an intensity that mirrors the moments just after the Big Bang. It is within these collisions that scientists unlock the doors to new particles, revealing secrets of the universe hidden from our everyday perception. When protons collide, they do not merely bounce off each other. They undergo a transformation. The energy from the collision can be so immense that it creates new particles from the very fabric of energy itself. This process is a vivid reminder of Einstein's famous equation, which tells us that energy and mass are interchangeable, like two sides of the same coin. In this high-energy environment, the standard rules of physics bend and twist, creating conditions where exotic particles can come into existence, albeit for fleeting moments. These events are not just random occurrences, they are opportunities for discovery, each collision a potential window into the unknown. Consider the landmark discovery of the Higgs boson, a particle that eluded scientists for decades. Its existence was hypothesized in the 1960s, but it remained elusive, a ghost in the subatomic world. The Higgs boson is often referred to as the God particle because of its profound implications for our understanding of mass. It is here that the collision events at the Large Hadron Collider played a pivotal role. Scientists meticulously designed experiments to collide protons under extreme conditions, hoping to catch a glimpse of this elusive particle. As protons collided at unprecedented energies, detectors were poised to capture the aftermath. Researchers scrutinized the data, sifting through the chaos of particles produced in the collisions. It was a monumental task, akin to finding a needle in a haystack. Yet, the persistence paid off. In July of 2012, scientists at CERN announced the discovery of a particle consistent with the Higgs boson. It was a moment of triumph, not just for the researchers involved, but for the scientific community as a whole. The Higgs boson's discovery was significant because it confirmed a crucial part of the Standard Model, the theoretical framework that describes the fundamental forces and particles in our universe. This breakthrough was not just a feather in the cap of particle physics, it had profound implications for our understanding of the universe. The Higgs boson provided an explanation for why particles acquire mass, a fundamental feature that shapes the very structure of matter. Without it, our universe would be a very different place, one devoid of atoms, stars, planets, and ultimately, life. The existence of the Higgs field, which permeates all of space, is what gives particles their mass, allowing them to clump together and form the structures we see around us. The discovery of new particles extends beyond the Higgs boson, venturing into the realm of exotic particles. These are particles that challenge our current understanding and push the boundaries of the Standard Model. As physicist Maria Goeppert-Mayer once said, "The most important thing is not to stop questioning." This ethos is at the heart of particle physics, where each new particle discovered invites further inquiry and exploration. Imagine the excitement that ripples through the scientific community with each new finding. Exotic particles can possess unique properties, such as unusual spins or interactions, that can offer insights into unexplored areas of physics. For instance, the search for dark matter, which is believed to make up a significant portion of the universe, has led scientists to explore particles beyond the Standard Model, such as WIMPs or axions. These particles, if found, could revolutionize our understanding of the cosmos. As we delve into the impact of new particles on the Standard Model, it is crucial to recognize that this framework is not static. It is a living document that evolves with each discovery. New particles can reveal inconsistencies within the model, prompting scientists to refine their theories and expand their understanding. The introduction of particles like the Higgs boson has led to further questions about the nature of mass and the forces that govern interactions between particles. Consider the implications of discovering particles that exhibit behaviors contrary to our current expectations. These anomalies can signal the need for new theories, potentially leading to a deeper understanding of the universe. The quest for knowledge is unending, and with each new particle, we inch closer to uncovering the mysteries of existence. Moreover, the implications of these discoveries extend beyond theoretical physics. They have practical applications that can reshape technology and enhance our understanding of the world. The innovations born from particle physics research, such as advancements in medical imaging or data analysis techniques, ripple through various fields, demonstrating the interconnectedness of scientific inquiry. In this ongoing journey, scientists continue to push the boundaries of what we know. Each collision at the accelerator represents not just a scientific experiment, but a bold step into the unknown. As we reflect on the significance of these discoveries, we are reminded of the words of physicist Richard Feynman, who expressed, "The important thing is not to stop questioning." This relentless pursuit of knowledge propels humanity forward, and the exploration of new particles is just one facet of this grand adventure. With every collision, we peel back layers of the universe, revealing its intricate design. It is a dance of energy and matter, a harmonious interplay that beckons us to ask deeper questions and explore further. The universe, in its silence, whispers its secrets to those willing to listen and seek. As we continue to explore this vast frontier, we remain ever curious, eager to uncover the wonders that lie beyond our current understanding. The journey is far from over, and the possibilities are as boundless as the cosmos itself. As we immerse ourselves in this fascinating world, the significance of discovering exotic particles becomes increasingly apparent. These particles, which lie beyond the familiar landscape of the Standard Model, can provide glimpses into realms of physics that we have yet to fully comprehend. Imagine a new particle that exhibits properties unlike anything previously observed, perhaps one that interacts with matter in unexpected ways or exists only under extreme conditions. Such discoveries challenge our current frameworks and invite us to rethink our understanding of the universe. The search for these exotic particles has ignited the imagination of physicists worldwide. Take, for example, the pursuit of supersymmetry, a theoretical framework suggesting that every particle has a heavier counterpart, known as a superpartner. This notion, if validated, could solve numerous enigmas about dark matter and the unification of forces. As physicist Nima Arkani-Hamed once reflected, the discovery of a new particle can change everything. With every potential new exotic particle, we inch closer to answering profound questions about the nature of reality itself. The impact of these discoveries on the Standard Model cannot be overstated. This model, while incredibly successful in describing a vast array of phenomena, is incomplete. It does not account for dark matter or dark energy, which together are thought to compose a significant portion of the universe. Each new particle discovered serves as a clue that could lead us to a more comprehensive understanding of these elusive components of the cosmos. Consider the implications of a particle that might mediate interactions we have yet to observe. Such a particle could potentially lead to new forces of nature, expanding our comprehension of how the universe operates. The very structure of the Standard Model could shift, leading to a paradigm where new forces coexist alongside gravity, electromagnetism, and the strong and weak nuclear forces. This expansion would not merely be a scientific curiosity. It could have profound implications for our understanding of the universe's origins and ultimate fate. One of the most tantalizing mysteries in particle physics is the nature of neutrinos. These ghostly particles, which barely interact with matter, are produced in copious amounts from the sun and during supernovae. Their elusive behavior can leave us pondering, what other phenomena exist that we have yet to detect? The study of neutrinos has already begun to reveal anomalies that challenge the standard model, hinting at the possibility of new physics. As we continue to conduct experiments with high-energy collisions, we may uncover new neutrino species or interactions, further enriching our understanding of the universe. Reflecting on the contributions of remarkable scientists throughout history, we can appreciate how their insights have shaped our journey. Enrico Fermi's work on weak interactions laid the groundwork for understanding neutrinos, while the contributions of others, like Murray Gell-Mann, who proposed the quark model, have opened doors to new realms of inquiry. Each discovery builds upon the last, forming a chain of knowledge that threads through time. Imagine standing in a laboratory, surrounded by the hum of machinery, the glow of screens displaying data that may contain the next big revelation. Each collision event captured is a moment of potential, a chance to witness the birth of a new particle. The excitement is palpable as researchers sift through mountains of data, employing sophisticated algorithms and machine learning techniques to identify patterns that may indicate a new discovery. This technological evolution is not merely an enhancement. It represents a paradigm shift in how we explore the subatomic realm. As we continue to push the boundaries of our understanding, we are reminded of the interconnectedness of science and technology. Innovations derived from particle physics research often find applications far beyond the laboratory. Take, for instance, the development of advanced imaging techniques used in medical diagnostics. The same principles that allow us to visualize particles colliding at high energies are employed in technologies that enable doctors to peer inside the human body, helping to save lives. Moreover, the collaborative efforts of international teams at large-scale facilities like CERN demonstrate the shared human endeavor in the pursuit of knowledge. Scientists from diverse backgrounds come together, united by a common goal: to unravel the mysteries of the universe. They embody the spirit of exploration as they work tirelessly to decode the data, analyze the results, and celebrate the triumphs, no matter how small. Each discovery, each new particle, becomes a shared victory, a testament to the power of collaboration. As we consider the landscape of particle physics and the discoveries that lie ahead, we are filled with a sense of wonder and anticipation. The collisions at the Large Hadron Collider and other facilities around the globe are not merely events. They are gateways to understanding the universe at its most fundamental level. With each new finding, we deepen our appreciation for the complexities of existence and the intricate dance of particles that compose the world around us. In this vast cosmos, the quest for knowledge is relentless. Each new particle discovered is a note in the symphony of science, harmonizing with the echoes of past discoveries. As we continue to explore, we are reminded that the universe is not just a collection of particles, but a rich tapestry of phenomena waiting to be understood. Each collision brings us closer to revealing the wonders that lie just beyond our current grasp, inviting us to dream, to question, and to seek. The journey continues, and so does our quest for the truth hidden in the depths of the cosmos. Chapter 6: Fundamental Forces and Particle Interactions. In the intricate dance of the universe, forces weave a profound narrative, governing the interactions of the particles that form the very fabric of existence. Each of these forces plays a vital role, shaping the destiny of particles, binding them together, or allowing them to transform and decay. Picture a grand stage where the elemental actors, quarks, electrons, and the forces that bind them, perform a captivating play, each move dictated by the invisible hands of fundamental forces. At the heart of this narrative lies the strong force, a powerful yet unseen entity that binds quarks together to create protons and neutrons. Imagine quarks as tiny, vibrant spheres, each carrying a fractional electric charge, dancing within the confines of a proton or neutron. The strong force, mediated by particles called gluons, acts like a glue that holds these quarks in a tight embrace. Without this force, the very structure of matter would unravel, and the universe as we know it would cease to exist. As we contemplate the strong force, we cannot help but reflect on the insights of pioneers like Richard Feynman, who famously described the interactions of particles as a game of marbles, where the rules are dictated by the nature of the forces at play. The strong force is not just a static entity, it is dynamic, manifesting in the vibrant interactions of quarks that produce an array of particles through their binding and unbinding. This force operates over a short range, yet its strength is unparalleled, capable of overcoming the electromagnetic repulsion between protons within the nucleus of an atom. Picture a tiny, dense nucleus composed of protons and neutrons held together by the strong force. It is within this nucleus that the magic of matter occurs, allowing atoms to form and subsequently give rise to the myriad substances we encounter daily. The strong force is what makes the sun shine. It facilitates the fusion of hydrogen atoms into helium, releasing tremendous energy that warms our planet and sustains life. As we turn our gaze to another fundamental force, we encounter the electromagnetic force, a pervasive and essential interaction that governs the behavior of charged particles. Imagine charged particles as tiny magnets, each exerting a force on one another, a ballet of attraction and repulsion. This force is responsible for the very structure of atoms, influencing how electrons orbit around the nucleus. The electromagnetic force is not merely a background player. It shapes the chemical interactions that allow for the formation of molecules, the building blocks of life. Consider the beauty of a water molecule, where two hydrogen atoms bond with an oxygen atom. This bond, a result of electromagnetic attraction, creates not only a vital substance for all living beings, but also plays a crucial role in the planet's climate and ecosystems. The electromagnetic force is a constant presence in our lives, dictating the interactions that occur between different elements and compounds, crafting the reality we experience. Yet, even as we marvel at the strong and electromagnetic forces, we must also acknowledge the weak force, a subtle yet influential player in the realm of particle interactions. This force is responsible for processes such as beta decay, where neutrons transform into protons, emitting electrons and neutrinos in the process. Imagine a neutron, a stable entity within the nucleus, suddenly undergoing transformation, shedding particles as it shifts into a proton. This transformation is not random. It is governed by the weak force, which operates over an incredibly short range and is only effective at the subatomic level. The implications of the weak force are profound, for it reveals the transient nature of matter itself. Through weak interactions, particles can decay, giving rise to new entities and altering the balance of particles in a system. This process is crucial in the realm of stellar evolution, impacting the life cycles of stars and, ultimately, the formation of elements in the universe. As physicist Steven Weinberg remarked, the laws of nature are not just what we see around us, they are also the processes that allow for change and decay. Imagine a universe where particles are static, unchanging. It would lack the vibrancy and dynamism that characterize our reality. The weak force introduces a rhythm of transformation, allowing for the birth of new particles and the gradual evolution of matter. This force is pivotal in the context of particle physics research, providing insights into the fundamental nature of particles and their interactions. The interplay between these fundamental forces creates a rich tapestry of interactions that define the behavior of particles. Each force contributes to a symphony of interactions, weaving a narrative that underpins the universe. From the binding strength of the strong force to the graceful movements of electromagnetic interactions and the subtle shifts of the weak force, these forces coalesce to form the intricate web of existence. As we explore the implications of these forces, we find ourselves contemplating the very nature of reality. What does it mean for particles to interact in such complex ways? How do these interactions shape the universe and our understanding of it? These questions invite us to delve deeper into the mysteries of the cosmos, where science and imagination converge. In the vast expanse of the universe, where galaxies swirl and stars are born, the fundamental forces guide the behavior and interactions of particles. These forces, though invisible, shape the structure of matter, the evolution of stars, and the very fabric of reality itself. They are the unseen architects of existence, crafting a world that, while profound in its complexity, invites us to explore and understand the nature of our universe. The strong force, electromagnetic force, and weak force each play a unique role in the symphony of particle interactions, allowing us to understand not just the individual components of matter, but also the larger structure of the universe itself. As we dive further into the implications of these forces, let us take a moment to consider how they interact with one another, creating a dynamic interplay that shapes the cosmos. In the realm of particle physics, the strong force is often perceived as the heavyweight champion, relentless in its ability to bind quarks together. Yet, it is the electromagnetic force that allows for the intricate relationships between charged particles. Imagine, if you will, a universe devoid of electromagnetic interactions. Without this force, atoms would not be able to attract or repel one another, and the very molecules that form everything around us, from the air we breathe to the water we drink, would not exist. When charged particles come together, they create a complex network of interactions that govern chemical bonding. Think of the elegant way in which a single oxygen atom can bond with two hydrogen atoms to form water, a molecule essential for life. This bonding is not merely a coincidence. It is the direct result of electromagnetic forces at play. The positive charge of the protons in the oxygen atom attracts the negative charge of the electrons in the hydrogen atoms, illustrating a delicate balance that gives rise to the familiar H2O. The electromagnetic force extends beyond just the formation of molecules. It is the very foundation of chemistry, dictating how atoms interact and combine. As you visualize the vast array of elements on the periodic table, consider how the electromagnetic force allows certain elements to bond easily while others remain inert. The noble gases, for instance, possess a full complement of electrons, rendering them stable and uninterested in forming bonds. In contrast, elements like sodium and chlorine are eager to combine, leading to the creation of table salt, a substance that is as ubiquitous as it is vital. As we contemplate the interplay of these forces, we must also recognize the profound implications of the weak force. This force, while subtle, plays a crucial role in the life cycle of stars. In the heart of a star, the conditions are extreme, with immense pressure and temperature. Within this fiery furnace, hydrogen atoms fuse to form helium, a process that releases vast amounts of energy. Yet, the weak force is essential for this process to occur. Through weak interactions, particles can transform, allowing for the conversion of one type of particle into another. This transformation is vital for the ongoing fusion processes that power stars, ultimately leading to the creation of heavier elements as stars age and evolve. Consider the life cycle of a massive star. Initially, it burns hydrogen in its core, but as hydrogen becomes scarce, the weak force allows for the conversion of helium into heavier elements, such as carbon and oxygen. This process is a testament to the dynamic nature of the universe, where transformation is not only possible but necessary for the evolution of matter. The weak force, with its ability to facilitate particle decay, ensures that the universe is not static, but a vibrant, ever-changing entity. The implications of the weak force extend beyond stellar evolution. It is also fundamental to understanding the processes that govern the early universe. During the moments following the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, the weak force played a critical role in shaping the interactions of these particles, leading to the formation of protons and neutrons. This laid the groundwork for the synthesis of elements in the primordial nucleosynthesis phase, offering a glimpse into how the cosmos evolved from a state of chaos into the structured universe we observe today. In the quest for knowledge, scientists have sought to unravel the mysteries of these fundamental forces. Through experiments conducted in particle colliders, researchers have probed the very fabric of reality, observing how these forces interact and influence the behavior of particles. The discoveries made in these laboratories are akin to unlocking ancient secrets, revealing insights that not only deepen our understanding of the universe, but also challenge our perceptions of reality. As we reflect on the contributions of pioneers in this field, we cannot overlook the work of individuals like Enrico Fermi, who advanced our understanding of the weak force and its implications for particle decay. Fermi's insights paved the way for the development of modern particle physics, allowing us to probe deeper into the nature of matter and the forces that govern it. His legacy serves as a reminder of the relentless pursuit of knowledge, where each discovery opens new avenues for exploration. The interplay between the strong force, electromagnetic force, and weak force creates a multidimensional landscape of interactions, weaving a rich narrative of existence. Each force not only contributes to the structure of matter, but also influences the processes that drive the evolution of the universe. This intricate web of interactions prompts us to ask, how do these forces shape the future of our cosmos? What new discoveries await us in our quest to understand the fundamental nature of reality? As we journey through this fascinating realm, we invite you to ponder the beauty of these forces at work. Picture the delicate balance of attraction and repulsion, the binding of particles creating stability, and the subtle transformations that pave the way for change. It is within this interplay that we find the essence of the universe, a dynamic and ever-evolving landscape of matter and energy. The story of fundamental forces and particle interactions is a testament to the complexity and wonder of the cosmos, inviting us to explore further and deepen our understanding of the world around us. Chapter 7: Theoretical Implications of Collider Experiments. Collider experiments serve as a profound testing ground for theoretical predictions that shape our understanding of the universe. Imagine, if you will, a vast cosmic puzzle, with each piece representing a fundamental aspect of our reality. The role of collider experiments is to fit these pieces together, to reveal the larger picture that lies beneath the surface of everyday experience. These experiments bring together the intricate theories of physics and the raw data produced by high-energy collisions. They allow scientists to confront their ideas with the unyielding truth of nature, illuminating the pathways that lead to new discoveries. As particles collide at nearly the speed of light, they create conditions that mimic the early universe, where the laws of physics as we know them were in a state of flux. Theoretical predictions, such as the existence of the Higgs boson or the properties of supersymmetry, necessitate experimental verification. Each collision event opens a window into the realms of possibility. It is a moment where theory meets reality. The excitement of scientists is palpable as they await results that could either confirm their predictions or challenge their understanding of the very fabric of existence. In the quest for physics beyond the standard model, collider experiments play a pivotal role. The standard model has served as a robust framework, successfully describing the electromagnetic, weak, and strong forces that govern particle interactions. Yet, it leaves a significant mystery unaddressed: the nature of dark matter and dark energy, which together make up approximately 95% of the universe. What might exist beyond the confines of this well-established model? This question has driven researchers to explore new theories, to search for phenomena that lie just beyond our current understanding. Consider the implications of dark matter, an invisible substance that does not emit light or energy, yet exerts gravitational influence on visible matter. How can we detect something we cannot see? Collider experiments provide potential avenues for discovery. Theories such as weakly interacting massive particles, or WIMPs, suggest that dark matter could consist of particles that interact via the weak force. As scientists collide particles at unprecedented energies, they hope to create conditions that allow these elusive dark matter candidates to reveal themselves. The potential discovery of a new particle that could account for dark matter would not only enhance our understanding of the universe, but also redefine our position within it. Equally enigmatic is dark energy, a force that drives the accelerated expansion of the universe. While its exact nature remains elusive, collider experiments could shed light on possible candidates that contribute to this phenomenon. Some theorists propose modifications to existing frameworks, suggesting that new particles or interactions may underlie dark energy. Imagine a scenario where collisions produce signatures of these interactions, offering a glimpse into the forces that shape the cosmos on grand scales. The results could transform our models of the universe, guiding us toward a deeper comprehension of its expansion and evolution. As we explore these theoretical implications, supersymmetry emerges as a significant contender in the search for new physics. A theory that posits each particle has a superpartner, supersymmetry aims to address several gaps in the standard model. It offers solutions to issues such as the hierarchy problem and the nature of dark matter. If supersymmetry exists, collider experiments may provide the first evidence of these superpartners, unlocking a new chapter in our understanding of the universe. The very act of smashing particles together may create conditions ripe for the emergence of these elusive entities, which could transform the way we perceive the fundamental structure of reality. String theory, another theoretical framework, offers a different perspective on the fundamental nature of particles. It posits that the basic building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. This elegant theory attempts to unify all fundamental forces, weaving them into a single framework. Collider experiments, while primarily focused on particle interactions, could also provide insights that resonate with string theory's implications. Imagine the possibility that the energy produced in collisions could reveal evidence of additional dimensions or the existence of hidden symmetries. Such discoveries would challenge our conception of space and time, pushing the boundaries of our understanding even further. As researchers eagerly await results from collider experiments, they are acutely aware of the profound implications these findings may have. Each collision is a moment of potential revelation, where the universe offers up its secrets to those willing to listen. Theoretical predictions guide the quest for knowledge, while experimental data provides the essential feedback loop that drives scientific inquiry. The interplay between theory and experiment shapes the trajectory of research. leading to a deeper appreciation of the mysteries that lie at the heart of existence. In this landscape of exploration, the importance of collaboration cannot be overstated. Scientists from diverse fields unite their expertise in a shared mission to unlock the secrets of the universe. Physicists, engineers, and computer scientists work together, each contributing their unique skills to the intricate tapestry of collider experiments. The synergy of these disciplines fosters an environment where innovative ideas can flourish, propelling the quest for knowledge forward. The excitement surrounding collider experiments is palpable, as researchers stand on the precipice of discovery. Will the results from these experiments confirm existing theories or challenge them in ways we cannot yet imagine? The anticipation hangs in the air, a reminder of the dynamic nature of scientific exploration. It is a testament to the human spirit's relentless pursuit of understanding, a journey that stretches across time and space. As we reflect on the theoretical implications of collider experiments, it becomes clear that our pursuit of knowledge is not merely about answering questions. It is about expanding our horizons. Each discovery sparks new inquiries, igniting the flame of curiosity that drives us to explore the unknown. In the vast expanse of the universe, where the boundaries of our understanding are continually pushed, collider experiments stand as beacons of hope, illuminating the path toward new realms of enlightenment. In this intricate dance between theory and experiment, we are reminded that the universe is not a static entity, but a vibrant landscape filled with possibilities. Theoretical predictions guide us, yet it is the experimental evidence that breathes life into these ideas. As we await the unfolding narrative of collider experiments, we embrace the uncertainty that accompanies the quest for knowledge, for it is within this uncertainty that the most profound discoveries await. As we immerse ourselves in the implications of collider experiments, we encounter a landscape rich with theories that beckon us to explore further. The search for physics beyond the standard model is a journey fueled by curiosity, and at its forefront lies the concept of dark matter. This elusive substance, which interacts with ordinary matter only through gravity, poses profound questions about the composition of the universe. Imagine the vastness of an ocean, where only the surface is visible while the depths remain obscured, teeming with unknown life. Dark matter is akin to this hidden realm, influencing the structure and formation of galaxies while remaining undetectable by conventional means. Theoretical physicists have proposed various candidates for dark matter, each presenting a distinct narrative to explain its mysterious nature. Among these, axions, sterile neutrinos, and the previously mentioned WIMPs stand out. Axions, for instance, are hypothetical particles that could solve several puzzles in particle physics, including the strong CP problem. They are predicted to be extremely light and weakly interacting, making them challenging to detect. Experimental efforts, including those at collider facilities, aim to create conditions where these particles could manifest. Consider what it would mean for our understanding of the universe if a collider experiment were to uncover evidence of axions or another form of dark matter. It would not merely be a discovery, it would be a paradigm shift. In parallel, the nature of dark energy continues to elude our grasp. This mysterious force, which contributes to the accelerated expansion of the universe, invites speculation and intrigue. Various theories attempt to explain its presence, from quintessence, a dynamic field that evolves over time, to modifications of gravity itself. Collider experiments could play a crucial role in testing these theories, as they may reveal new particles or interactions that challenge our current understanding of cosmic expansion. Picture the universe as a balloon being blown up, with dark energy acting as the breath that inflates it. Each collision within a collider might yield insights into the mechanics of this expansion, paving the way for a more comprehensive understanding of the cosmos. Supersymmetry, a cornerstone of many theoretical explorations, holds promise as a key player in this quest. This theory postulates that every particle in the Standard Model has a superpartner, which could help stabilize the mass of the Higgs boson and address the hierarchy problem. The potential discovery of these superpartners has been a driving force in collider experiments. Imagine the thrill of physicists as they analyze collision data, searching for signatures that could indicate the presence of these elusive entities. If supersymmetry were confirmed, it would not only enrich our understanding of particle physics, but could also provide candidates for dark matter, intertwining these two great mysteries of the universe. String theory, with its elegant proposition of one-dimensional strings as the fundamental components of reality, offers yet another avenue for exploration. This framework aims to unify the four fundamental forces of nature, weaving them into a coherent tapestry. Collider experiments may one day provide evidence supporting the existence of additional dimensions, as predicted by string theory. Envision a realm where the familiar three dimensions of space are complemented by hidden dimensions curled up in ways we cannot yet perceive. The energy produced in high-energy collisions could resonate with these hidden dimensions, leading to discoveries that stretch our understanding of the universe to its very limits. The implications of collider experiments extend beyond mere particle detection. They challenge our very notions of reality. As scientists sift through mountains of data, they confront the tantalizing possibility that our understanding of time, space, and matter could be fundamentally altered. Researchers like Feynman and others have urged us to embrace the unknown, to remain open to ideas that may seem implausible at first. This spirit of inquiry fosters an environment where radical theories can flourish, pushing the boundaries of what we believe to be possible. In this ever-evolving landscape, collaboration remains essential. The confluence of ideas from physicists, mathematicians, and engineers fuels the transformative power of collider experiments. Each discipline contributes unique perspectives, enhancing the collective understanding of complex phenomena. The synergy of these diverse fields fosters creativity, encouraging scientists to think beyond traditional paradigms. Picture a team of researchers gathered around a console, analyzing collision data with the fervor of explorers charting uncharted territory. Their discussions and debates illuminate the path forward, revealing new questions and avenues for investigation. As we ponder the future of collider experiments, we are reminded that the pursuit of knowledge is an ongoing journey. Each discovery, whether it confirms or challenges existing theories, propels us deeper into the mysteries of the universe. The dance between theory and experimental evidence continues to unfold, revealing a cosmos that is as intricate as it is awe-inspiring. The questions we ask today shape the inquiries of tomorrow, urging us to explore the vast expanse of the unknown. In this delicate balance of curiosity and discovery, we find ourselves at the edge of understanding. Collider experiments serve as a beacon, guiding us through the dark waters of uncertainty toward the light of knowledge. The potential outcomes of these experiments are limitless, each collision a doorway to new realms of understanding. Will we uncover the secret of dark matter, or perhaps glimpse the nature of dark energy? The possibilities lie before us like stars scattered across the night sky, each twinkling with the promise of discovery. As we await the results from these monumental experiments, we hold our breath, savoring the tension that accompanies the pursuit of knowledge. The universe, with all its mysteries, beckons us to venture further, to question, and ultimately to understand. The journey continues, an exhilarating expedition into the heart of existence, where every collision might just hold the key to unlocking the profound secrets of the cosmos. Chapter 8: The Future of Particle Physics Research. The future of particle physics research stands on the precipice of remarkable advancements, promising a new era of discovery that could reshape our understanding of the universe. Imagine a horizon where next-generation colliders, equipped with cutting-edge technology, unlock the mysteries that have eluded scientists for decades. Projects like the Future Circular Collider, proposed to be built near Geneva, aim to push the boundaries of energy levels beyond what we have currently achieved. This colossal endeavor would allow researchers to explore the properties of the Higgs boson with unprecedented precision, and even probe for hypothetical particles predicted by theories beyond the standard model. As scientists envision these advancements, they are driven by the tantalizing possibility of unearthing new particles and interactions that could challenge our current theories. What if we discovered a particle that could provide insights into dark matter, that elusive component believed to make up a significant portion of the universe's mass? The implications of such a discovery are profound. It could lead us to rethink the very fabric of reality, reshaping our understanding of cosmic evolution and the fundamental forces at play. In this context, we can also consider the implications of exploring supersymmetry, a theoretical framework that posits every particle has a superpartner. If experiments at these upcoming colliders could reveal evidence supporting this theory, it would mark a pivotal moment in particle physics, bridging gaps in our current understanding and inspiring future generations of scientists. However, the journey into this exciting future is not a solitary endeavor. International collaboration plays a crucial role in advancing research in particle physics. The global nature of science today means that groundbreaking projects like the Large Hadron Collider were not built by a single nation, but through the combined efforts of scientists from around the world. This spirit of collaboration fosters a diverse exchange of ideas and resources, enhancing our collective capacity to tackle the universe's most pressing questions. Consider the fact that the LHC, one of the largest and most complex scientific instruments ever built, required contributions from thousands of scientists and engineers spanning multiple disciplines. This collaborative approach leads to innovation as different perspectives come together to solve complex challenges. With the establishment of new facilities like the International Linear Collider, the framework for international cooperation continues to expand, inviting scientists from various backgrounds to contribute their expertise. Yet, as the landscape of particle physics research evolves, so too do the challenges that lie ahead. Funding remains a critical concern, as the pursuit of knowledge often competes with immediate societal needs. The enormity of financial investment required for these advanced projects can be daunting. The question emerges: how do we inspire both public interest and support for the scientific endeavors that enhance our understanding of the universe? Engaging the public in the narrative of particle physics, the quest to understand the building blocks of existence, becomes essential. Imagine the stories we can tell about the cosmic dance of particles, the interconnectedness of all matter, and the profound implications of our discoveries. By fostering a sense of wonder about the universe, we can cultivate a culture that values scientific inquiry and supports the funding necessary to sustain it. Additionally, the challenge of public interest extends beyond mere financial support. As particle physics delves into concepts that can seem abstract and distant, it is imperative to communicate these ideas in ways that resonate with people's everyday experiences. How can we make the invisible world of subatomic particles relatable? Perhaps by illustrating how particle physics informs technologies we rely on daily, from medical imaging techniques to advancements in computing and telecommunications, can bridge the gap between scientific research and public understanding. As we step into this future, the collective pursuit of knowledge continues to inspire awe and curiosity. The advancements in collider technology, the potential for groundbreaking discoveries, the spirit of international collaboration, and the challenges of funding and public engagement weave together a narrative that propels us forward. Each step taken in this journey leads us closer to answering the profound questions that have intrigued humanity for centuries. What lies beyond our current understanding? What new chapters in the story of the universe await us? The answers lie ahead, waiting to be uncovered. As we turn our gaze toward the future of collider technology, it becomes clear that the upcoming projects represent not just an evolution of existing facilities, but a revolution in how we approach the mysteries of the universe. The Future Circular Collider, for instance, aims to be the successor to the Large Hadron Collider, increasing the collision energy and enhancing our sensitivity to rare processes. This leap in technology is akin to upgrading from a standard telescope to a powerful space telescope, allowing scientists to observe phenomena previously obscured by the limits of energy and precision. Consider the engineering marvel that such a collider would embody. It would comprise thousands of superconducting magnets, each crafted with meticulous precision to bend and focus particle beams. Imagine a network of cryogenic systems that maintain these magnets at temperatures colder than deep space, ensuring that they function flawlessly. This technological advancement is not merely about size or speed. It represents a leap into a realm of possibilities. With higher energies, we could explore the very edges of the standard model and venture into theories that seek to unify the forces of nature, potentially revealing insights into the enigmatic nature of dark energy. The potential discoveries that await us at these new facilities are tantalizing. What if we could detect particles that hint at the existence of extra dimensions? The idea that our universe could be just a three-dimensional slice of a much larger, multi-dimensional reality is a captivating one. The implications could be staggering, reshaping our fundamental understanding of space and time. Scientists have long speculated about the existence of gravitons, hypothetical particles that mediate the force of gravity. The ability to discover such particles could revolutionize our comprehension of gravity itself and its relationship with the other forces of nature. Moreover, the specter of new physics looms larger as we contemplate the implications of discoveries such as the Higgs boson. While its discovery was a monumental achievement, it also raised more questions than answers. The Higgs boson is but one piece of a complex puzzle. What if future experiments reveal additional scalar particles that could hint at mechanisms behind electroweak symmetry breaking? Such revelations would push the boundaries of our understanding and ignite a surge of new theoretical developments. At the heart of these advancements lies international collaboration, a cornerstone of modern scientific research. The diverse tapestry of cultures, ideas, and expertise that scientists bring to the table enriches the field of particle physics. The synergy created through shared goals and resources fosters an environment ripe for innovation. Scientists from various backgrounds contribute their unique perspectives, leading to breakthroughs that no single institution could achieve alone. Take, for instance, the collaboration behind the Large Hadron Collider, which involved thousands of scientists from over 100 countries. This monumental effort exemplifies how diverse expertise can converge to tackle the universe's most profound questions. The upcoming International Linear Collider similarly invites global participation, aiming to create an inclusive atmosphere where scientists can share their insights and collaborate on pressing challenges. Yet, as we journey into this promising future, we must confront the challenges that loom on the horizon. Funding is a perennial concern, often dictated by shifting political landscapes and competing priorities. The immense costs associated with building and maintaining such advanced facilities can deter investment, leading to a precarious balance between scientific ambition and fiscal responsibility. How do we convey the importance of particle physics research to the public and policymakers? The answer lies in storytelling, the ability to weave the intricate narratives of discovery, curiosity, and the quest for knowledge into a tapestry that resonates with people. By illustrating how particle physics underpins technologies that permeate our daily lives, such as medical imaging and advancements in computing, we can kindle a sense of connection to the research. Imagine a world where every child grows up understanding that the principles of particle physics contribute to the very devices they use, the medicines they take, and the technologies that facilitate their education. This awareness fosters an appreciation for science and its role in shaping our world, creating a supportive climate for funding and research. The challenge of sustaining public interest extends beyond mere funding. It calls for a commitment to education and outreach. As the language of particle physics can often seem esoteric, scientists have a responsibility to communicate their work in relatable terms. How can we bridge this gap? By embracing creativity and utilizing multimedia platforms, scientists can bring the invisible world of particles into the public eye, sparking curiosity and engagement. In this endeavor, the spirits of great scientists past inspire us. Their dedication and passion illuminate the path forward. They remind us that the pursuit of knowledge is a collective journey, one that transcends borders and generations. Each question we ask invites new inquiries, urging us to explore deeper and broader. As we embark on this exciting chapter of particle physics research, we stand at the threshold of profound discoveries, united by a shared vision of understanding the universe. The advancements in collider technology, the potential for groundbreaking revelations, the spirit of international collaboration, and the challenges of funding and public engagement interlace to create a narrative of hope and curiosity. What new revelations await us as we turn our eyes toward the cosmos? The journey continues, driven by the insatiable thirst for knowledge that defines our humanity. The future circular collider is not merely a structure of metal and magnets. It embodies the dreams and aspirations of countless physicists dedicated to uncovering the universe's secrets. This ambitious project aims to achieve collision energies that far exceed those of its predecessor, the Large Hadron Collider. As we imagine the immense scale of this endeavor, we can picture a network of tunnels, intricately designed to accommodate the complexities of particle interactions. Each segment of the collider represents a meticulous effort to enhance our understanding of fundamental forces, pushing the envelope of what we know about the universe. As we gaze forward, the potential discoveries await at these advanced facilities are nothing short of exhilarating. The prospect of finding particles that could elucidate the nature of dark matter tantalizes scientists. Dark matter, an unseen component that exerts gravitational influence on galaxies, remains one of the most profound mysteries in astrophysics. If future experiments lead us to the elusive particles that make up dark matter, it would not only revolutionize our understanding of the cosmos, but also affirm the interconnectedness of all matter and energy. Moreover, we are reminded of the words of renowned physicist Albert Einstein, who once said that the most beautiful experience we can have is the mysterious. This sentiment captures the essence of what drives particle physicists, the quest to unveil the unknown. What if we could discover evidence that supports the existence of extra dimensions or validate theories that unify the fundamental forces? Such findings would challenge our current paradigms and inspire a new generation of thinkers to explore the far reaches of scientific inquiry. In addition to the technological advancements in collider design, the role of international collaboration cannot be overstated. The future of particle physics is a collective endeavor, transcending borders and cultures. As scientists from various countries come together to pool their resources and expertise, they create a fertile ground for innovation. The International Linear Collider, for instance, is a testament to this collaborative spirit, drawing upon a global network of physicists and engineers. Imagine the vibrant discussions taking place in research facilities around the world, where diverse perspectives converge to tackle complex challenges. This exchange of ideas not only fosters creativity, but also promotes a shared sense of purpose. The contributions of scientists from different backgrounds enrich the research, allowing for breakthroughs that would be unattainable in isolation. Yet, as we envision this bright future, we must also confront the challenges that lie ahead. Funding remains a critical issue in the pursuit of particle physics research. The substantial financial investments required for these large-scale projects often compete with immediate societal needs. Consequently, how do we effectively convey the importance of these endeavors to the public and policymakers? Engaging the public in the narrative of particle physics is essential for garnering support. The stories we share about scientific discovery should evoke a sense of wonder and curiosity. Imagine explaining how the pursuit of knowledge about the universe leads to technological innovations that enhance everyday life, medical imaging techniques, advancements in computing, and even the development of materials used in everyday products. By connecting the dots between abstract scientific concepts and tangible benefits, we can inspire a broader appreciation for particle physics. Furthermore, the challenge of sustaining public interest in particle physics calls for a commitment to education and outreach. As scientists strive to communicate their work in accessible terms, they can bridge the gap between complex theories and everyday experiences. How can we make the intricate world of subatomic particles relatable? Perhaps by utilizing engaging visualizations, interactive exhibits, and community outreach programs, we can spark curiosity and encourage future generations to explore the wonders of the universe. As we consider the path that lies ahead in particle physics, we recognize that the advancements in collider technology, the potential for groundbreaking discoveries, the spirit of international collaboration, and the challenges of funding and public engagement form an interconnected web. Each element plays a vital role in shaping the future of this field, driving us toward a deeper understanding of the cosmos and our place within it. What discoveries await us as we journey forward? The tapestry of possibilities unfolds with each new experiment, inviting us to ponder the mysteries that lie just beyond the horizon. Together, as a global community united by a shared thirst for knowledge, we embark on an exciting quest to uncover the universe's secrets, one particle at a time. Chapter 9: Ethical Considerations in Particle Physics. As we explore the intricate world of particle physics, we encounter not just the marvels of discovery, but also the profound ethical questions that accompany large-scale scientific experiments. Imagine standing at the threshold of a vast underground collider, a monumental structure designed to probe the very essence of matter. Each experiment conducted within its colossal walls does not merely unveil the secrets of the universe. It also prompts us to reflect on the ethical implications of such endeavors. What responsibilities do scientists bear when harnessing the power of nature on such an immense scale? The enormity of particle colliders like the Large Hadron Collider often raises concerns about environmental impact. As particles are accelerated to nearly the speed of light, the energy consumed is staggering. Picture the vast amounts of electricity required to operate these machines, generated from diverse sources, some of which may have adverse environmental effects. Scientists are increasingly aware of the carbon footprint associated with such operations and are striving to develop sustainable practices. For instance, what if the energy for these experiments could be derived from renewable sources? This shift would not only mitigate environmental damage, but also set a precedent for future scientific endeavors, intertwining progress with ecological stewardship. Moreover, the safety protocols surrounding these experiments are paramount. The public safety measures in place reflect a commitment to transparency and responsibility. Imagine a community living in close proximity to a collider, their lives intertwined with the workings of this scientific marvel. It is essential for scientists to communicate effectively with the public, addressing concerns and sharing knowledge. What measures are taken to ensure that the risks involved are minimized? Through rigorous safety protocols, regular inspections, and comprehensive emergency response plans, researchers work diligently to mitigate any potential hazards. In this realm, the dialogue between scientists and the community fosters trust and understanding, essential components in navigating the complexities of ethical responsibilities. As we delve deeper into the ethical considerations, we must also reflect on the balance between scientific progress and ethical responsibilities. The pursuit of knowledge often pushes boundaries, leading to groundbreaking discoveries that can transform our understanding of the universe. Yet, with each leap forward, we must ask ourselves, at what cost? The ethical landscape is fraught with dilemmas, particularly as we confront the implications of our findings. For example, consider the potential applications of particle physics, research in medicine, or technology. Advancements in imaging techniques and cancer treatments have emerged from this field, showcasing the beneficial ripple effects of scientific inquiry. However, the dual-use nature of such technologies raises questions about their potential misuse. It challenges us to consider how we can promote scientific advancement while safeguarding against ethical pitfalls. The legacy of outstanding individuals in the field of particle physics also plays a significant role in shaping our ethical framework. Think of the visionaries who have dedicated their lives to understanding the universe, often at great personal sacrifice. Many have expressed the belief that science should serve humanity, a sentiment echoed by the likes of Enrico Fermi. He once stated that a scientific man should be able to make a correct estimate of the future consequences of his actions. This perspective invites us to examine how we can honor the legacies of these pioneers by embedding ethical considerations into the very fabric of scientific exploration. In this context, we can also consider the moral implications of pursuing knowledge that may lead to unforeseen consequences. The discovery of new particles or forces, while exhilarating, carries the weight of responsibility. What if a breakthrough leads to technologies that could be misused or that alter our environment in irreversible ways? These questions compel us to engage in a reflective dialogue about the purpose and direction of our research. It is an invitation to explore how we can align our scientific endeavors with the broader goals of societal well-being. Furthermore, the intersection of particle physics and public policy underscores the ethical dimensions of research. As funding for large-scale experiments often comes from public sources, there exists a moral obligation to ensure that the research aligns with the interests of society. Imagine a future where the public is not merely a passive observer, but an active participant in shaping scientific agendas. This vision encourages a collaborative approach, where scientists and citizens come together to discuss the implications of research and establish priorities that reflect the values and concerns of the community. As we journey through the ethical landscape of particle physics, we must also grapple with the tension between innovation and precaution. Scientists are often driven by an insatiable curiosity to explore the unknown. Yet, this pursuit must be tempered with a responsibility to consider the potential consequences of their discoveries. The balance between scientific ambition and ethical considerations is delicate, requiring constant vigilance and reflection. In this ever-evolving field, the dialogue surrounding ethics must remain dynamic, adapting to new challenges and discoveries that emerge from the depths of the universe. The exploration of particle physics is not merely an academic pursuit. It is a profound journey into the heart of existence itself. As we push the boundaries of knowledge, we must remain steadfast in our commitment to ethical principles. It invites us to envision a future where scientific discovery is not only celebrated, but also guided by a deep sense of responsibility. Each experiment, each collision, carries the weight of our ethical obligations, shaping not only our understanding of the universe, but also our role within it. In this regard, the legacy of ethical considerations in particle physics will define the trajectory of future research. The choices we make today have the potential to resonate throughout generations, influencing how science interacts with society and the environment. As we contemplate the vast possibilities that lie ahead, let us embrace the challenges and opportunities that come with this remarkable field. The path forward is illuminated by the commitment to ethical exploration, a guiding light that will lead us to discoveries that not only enrich our understanding of the universe, but also honor the profound responsibilities that accompany them. The ethical landscape of particle physics is complex, woven together with the threads of innovation, responsibility, and societal impact. As we continue to explore this intricate terrain, we encounter the profound ethical questions surrounding large-scale scientific experiments. The dilemma arises not only from the experiments themselves, but also from the broader implications they hold for humanity and the environment. What happens when the quest for knowledge clashes with the potential for unintended consequences? Imagine a scenario in which a breakthrough experiment reveals a new particle that could lead to revolutionary technology. This discovery could provide unprecedented energy solutions or medical advancements. Yet, the same knowledge could also pave the way for misuse or environmental degradation. A poignant example can be found in the development of nuclear technology, which, while initially promising, ultimately led to both remarkable advancements and catastrophic consequences. The dual nature of scientific discovery urges us to tread carefully, weighing the benefits against the possible hazards that lie ahead. In light of such considerations, the environmental impact of particle colliders demands our attention. These colossal machines, while gateways to understanding the universe, consume enormous amounts of energy. Picture the sprawling facilities, their vast networks of cooling systems and power sources working tirelessly to maintain the delicate balance required for experiments. The energy demands are immense, and as scientists become more conscious of their carbon footprints, they are compelled to seek sustainable alternatives. What if the power used to propel particles could be sourced entirely from renewable energy? This perspective not only highlights the urgency of environmental stewardship, but but also challenges the scientific community to innovate in ways that align with ecological sustainability. As we contemplate the environmental implications, we can also reflect on the historical context of scientific practice. The early days of particle physics were marked by a fervent belief in the unbridled pursuit of knowledge, often overshadowing concerns about the environmental repercussions. Yet, pioneers like Lise Meitner, who contributed significantly to nuclear physics, also advocated for the responsible use of scientific advancements. Her reflections remind us of the importance of ethical considerations in guiding the direction of research. How can we honor such legacies while striving for progress? The safety protocols that govern particle collider operations are a testament to the commitment to public safety. Imagine the meticulous planning that goes into every experiment, where scientists work in tandem with safety experts to devise comprehensive protocols. These measures are not merely bureaucratic necessities. They reflect a deep-seated responsibility to protect both researchers and the surrounding communities. The question arises: how do we ensure that the public feels secure and informed about the experiments conducted in their vicinity? Open communication and education play pivotal roles in this dynamic. By fostering dialogue, scientists can demystify their work and build trust, empowering communities to engage with the science that shapes their lives. As we delve further into the ethical considerations, we encounter the delicate act of balancing scientific progress with ethical responsibilities. The allure of discovery often tempts researchers to push boundaries, yet each stride forward must be anchored in a commitment to ethical integrity. The scientific community is increasingly recognizing the importance of ethical review boards, which serve to evaluate the potential risks and benefits of proposed experiments. This proactive approach is essential, yet it raises questions about the criteria used to assess what is deemed acceptable. Are we sufficiently equipped to weigh the long-term consequences of our actions? The landscape of particle physics also necessitates an exploration of how societal values influence scientific priorities. The advent of participatory science, where community input shapes research agendas, opens new avenues for collaboration. Imagine citizens actively contributing to discussions about the direction of scientific inquiry, ensuring that their voices are heard in decision-making processes. This paradigm shift not only democratizes science, but also enriches the ethical discourse by integrating diverse perspectives. In considering the future of particle physics, we must remain vigilant in our ethical considerations. The pursuit of knowledge should not exist in a vacuum. It must be grounded in a framework that prioritizes the well-being of society and the environment. As we stand on the brink of new discoveries, the responsibility rests on our shoulders to maintain an ethical compass that guides our exploration. In this journey, the call for accountability resonates deeply. Scientists are not merely explorers of the unknown, they are stewards of knowledge, tasked with navigating the complexities of their discoveries. This stewardship is not just about ensuring safety or minimizing environmental impact. It encompasses the broader implications of how scientific advancements intersect with the fabric of human experience. As we envision the future of particle physics, we are invited to imagine a world where scientific inquiry flourishes alongside ethical integrity. What if our pursuit of knowledge could harmonize with the values of justice, sustainability, and equity? This vision invites us to embrace the challenges of ethical inquiry as we forge ahead in our quest to unravel the mysteries of the universe. The legacy of particle physics is still being written, and the choices made by today's scientists will echo through generations. Each experiment conducted in pursuit of understanding carries with it a responsibility. A responsibility not only to the scientific community, but to humanity at large. By weaving ethical considerations into the very fabric of research, we can ensure that our quest for knowledge is not just a journey of discovery, but a journey that honors the interconnectedness of all life on Earth. As we reflect upon these considerations, the call to action becomes clear. The exploration of particle physics is not merely an academic endeavor. It is a profound responsibility that requires a thoughtful dialogue between science and society. In this vibrant interplay, we find the potential to illuminate the path forward, where the wonders of the universe can be uncovered while nurturing the ethical imperatives that guide us in our shared existence. Chapter 10: The Legacy of Particle Colliders in Science. In the sprawling history of particle colliders, we find an extraordinary tapestry of discovery, woven from the threads of human curiosity and scientific endeavor. As we reflect on the key discoveries made through these monumental machines, we come to appreciate their profound influence on our understanding of the universe. The Higgs boson, for instance, stands as a testament to the power of colliders, revealing insights into the very mechanism that gives mass to fundamental particles. Imagine a world where the mass of everything, from the tiniest atoms to colossal galaxies, remains a mystery. The discovery of the Higgs not only illuminated this issue, but also validated decades of theoretical predictions, drawing a vivid connection between the abstract world of mathematics and the tangible reality of existence. Yet, the legacy of particle colliders extends beyond single particles or phenomena. The study of neutrinos, elusive and mysterious, has gained momentum through collider experiments. These ghostly particles, once thought to be nearly impossible to detect, have unveiled secrets of the universe's energy balance. Picture the faint traces of neutrinos skimming through the Earth, barely interacting with matter, yet holding vital clues about the processes of stars and the workings of the universe. The data harvested through colliders has enhanced our understanding of these enigmatic particles, leading to advancements in both theoretical and experimental physics. Moreover, colliders have played a crucial role in refining our comprehension of fundamental forces. The intricate interactions between particles, governed by the strong, weak, and electromagnetic forces, have been elucidated through collider experiments. Scientists have been able to probe the behavior of quarks and gluons under extreme conditions, echoing the early moments of the universe when these particles danced in a primordial soup. This exploration is akin to peering into the very cradle of existence, revealing how the universe evolved from chaos into the structured cosmos we inhabit today. As we ponder the impact of collider research, we must also consider its ripple effects on technology and society. The innovations born from the exigencies of particle physics have transcended the realm of scientific inquiry, infiltrating various aspects of daily life. For instance, the technology developed for data analysis in collider experiments has found applications in fields as diverse as medical imaging and information technology. Imagine the sophisticated algorithms designed to sift through mountains of data, identifying patterns and anomalies, now enhancing diagnostic techniques in healthcare. This synergy between fundamental research and practical application illustrates the profound interconnectedness of science and society. The Internet itself owes a nod to the needs of physicists at CERN, where the World Wide Web was initially conceived as a means to facilitate information sharing among scientists. Today, this digital framework underpins our modern communication, a testament to how inquiries into the subatomic can yield transformative societal advancements. In a world where knowledge fuels progress, the legacy of colliders serves as a reminder that the pursuit of understanding can lead to unforeseen innovations that resonate far beyond the confines of the laboratory. Education and outreach play an indispensable role in this narrative, bridging the gap between complex scientific concepts and public understanding. The excitement generated by collider experiments can inspire the next generation of scientists. Imagine children, eyes wide with wonder, as they learn about the mysteries of the universe and the machines designed to unlock them. Engaging young minds through interactive exhibits and educational programs can foster a curiosity that fuels a lifelong passion for science. When children see that the same principles governing the universe also apply to their everyday lives, they become more than just passive observers. They become active participants in the unfolding story of discovery. Institutions around the world have embraced this responsibility, aiming to demystify the complexities of particle physics. Outreach initiatives often include public lectures, workshops, and exhibitions showcasing the wonders of colliders. Engaging with the community not only cultivates a sense of shared knowledge, but also emphasizes the importance of scientific literacy in an increasingly complex world. As physicist Brian Cox eloquently stated, "We are the cosmos made conscious, and life is the means by which the universe understands itself." In this light, the role of education becomes paramount, allowing individuals to grasp their place within the cosmic narrative. Looking ahead, the quest for knowledge continues to evolve, with particle colliders standing at the forefront of scientific exploration. Future endeavors promise to delve even deeper into the mysteries of the universe. As scientists prepare for the next generation of colliders, like the anticipated future circular collider, we can envision a landscape where the boundaries of our understanding are pushed further than ever before. These new machines are expected to reach unprecedented energy levels, opening doors to phenomena that current technology can only hint at. What might we discover in this uncharted territory? Could we finally unveil the nature of dark matter, that elusive substance believed to comprise a significant portion of the universe, yet remains undetectable? The implications of such discoveries could fundamentally alter our understanding of cosmology, unraveling the intricate tapestry of the universe's evolution. Moreover, the exploration of supersymmetry, a theoretical framework that predicts a partner particle for every known particle, could illuminate new avenues of research. Imagine a world where symmetry reigns supreme, where every particle is accompanied by its shadow. This concept not only tantalizes physicists with the promise of new particles, but also offers solutions to some of the most profound questions that remain unanswered in particle physics. The legacy of particle colliders thus extends into the realm of possibilities, a beacon guiding us toward a future rich with discovery. The journey of understanding, fueled by the immense energy of colliders and the relentless curiosity of scientists, is a testament to the human spirit. Each experiment, each collision, and each discovery adds another layer to our comprehension of the cosmos, a legacy that inspires generations to come. As we contemplate the vastness of the universe and the intricate details that define it, we are reminded that our pursuit of knowledge is an ongoing adventure. The legacy of particle colliders is not merely a collection of past achievements. It is a living, breathing narrative that continues to unfold. With each new inquiry, each new hypothesis, we inch closer to the answers that have eluded us for so long, weaving our understanding into the fabric of the cosmos itself. The legacy of particle colliders is a testament to the synergy between scientific inquiry and technological advancement. As we reflect on the impact of collider research, we must recognize how it has shaped not only our understanding of fundamental physics, but also the very fabric of our everyday lives. One of the most profound effects has been the development of cutting-edge technologies that stem from the challenges faced within the world of particle physics. Consider the advancements in imaging technology, particularly in medical diagnostics. The techniques pioneered for tracking and analyzing the vast amounts of data generated in collider experiments have given rise to sophisticated imaging systems used in hospitals worldwide. Imagine a patient lying in a scanning device, where the intricate algorithms initially designed to decipher the chaos of particle collisions are now working to unveil the hidden complexities of the human body. This cross-pollination of knowledge showcases the unexpected ways in which scientific endeavors can benefit society at large. Furthermore, communication technology has undergone a transformation rooted in the innovations of collider research. The World Wide Web, a cornerstone of modern communication, was born out of the necessity for physicists to share data efficiently. Its creation has fundamentally altered how we connect, learn, and disseminate information. Imagine the world before the internet, a time when knowledge was confined to books and papers. Today, a wealth of information is available at our fingertips, allowing ideas to flow freely across borders and cultures. This democratization of knowledge is inextricably linked to the collaborative spirit fostered by scientific research. The role of education and outreach in promoting science cannot be overstated. Institutions dedicated to advancing our understanding of the universe have embraced the responsibility of inspiring future generations. Programs designed to engage young minds often incorporate interactive experiences that demystify complex scientific concepts. Picture a group of students gathered around a virtual reality simulation, where they can witness the collision of particles as if they were standing in the heart of a collider. Such immersive experiences cultivate a sense of wonder and curiosity, inviting students to explore the mysteries of physics in a hands-on manner. Additionally, public lectures and community outreach initiatives serve to bridge the gap between scientists and the public. Engaging discussions, often led by passionate researchers, illuminate the significance of collider experiments and their implications for our understanding of the universe. Imagine the excitement in a room filled with curious individuals, all eager to learn about the latest discoveries and the science behind them. These interactions not only foster scientific literacy, but also cultivate a sense of shared ownership over the quest for knowledge. As we look to the future, the ongoing quest for understanding continues to evolve. The next generation of particle colliders promises to delve even deeper into the fabric of reality, unlocking new realms of exploration. Facilities like the Future Circular Collider are on the horizon, poised to push the boundaries of our current understanding. What new insights await us? The pursuit of knowledge is an unending journey, and each discovery serves as a stepping stone toward a more profound comprehension of the cosmos. Imagine the tantalizing possibilities of uncovering the nature of dark matter through these new experiments. Dark matter, which is believed to account for a substantial part of the universe's mass, remains an enigma that beckons researchers to unravel its secrets. The potential to identify new particles tied to dark matter could reshape our understanding of cosmic evolution, offering fresh perspectives on the universe's structure and behavior. Moreover, the exploration of phenomena such as extra dimensions and the unification of forces remains a tantalizing frontier. Theoretical frameworks like string theory suggest that our universe may harbor dimensions beyond the familiar three of space and one of time. What if collider experiments could provide evidence for these dimensions? The implications would be staggering, fundamentally altering our grasp of reality itself. As we journey further into this realm of inquiry, we are reminded of the words of Carl Sagan, who said, "Somewhere, something incredible is waiting to be known." This sentiment encapsulates the essence of scientific exploration, where each question leads to new mysteries and each answer opens the door to further inquiries. The legacy of particle colliders is not merely a collection of past triumphs. It is a vibrant narrative that continues to unfold, driven by the relentless curiosity of those who seek to understand the universe. In this ever-expanding landscape of discovery, the role of collaboration becomes increasingly vital. Scientists from diverse disciplines come together, pooling their expertise to tackle the complex questions that arise from collider research. This spirit of cooperation fosters innovation, as ideas and techniques cross-pollinate, leading to breakthroughs that may not have been possible in isolation. The collective endeavor of physicists, engineers, and educators creates a symbiotic relationship where knowledge flourishes and new pathways emerge. As we contemplate the challenges that lie ahead, we are also called to reflect on the ethical dimensions of our pursuit of knowledge. With each advancement comes a responsibility to ensure that our scientific endeavors align with the broader goals of society. How do we balance progress with sustainability? The quest for understanding must be accompanied by a commitment to ethical practices, ensuring that our pursuit of knowledge does not come at the expense of our planet or future generations. The legacy of particle colliders, therefore, is not just confined to the realm of physics. It extends into the very heart of our society. It challenges us to think critically about our role in the universe and our responsibility to one another. As we stand on the precipice of new discoveries, we are reminded that the journey of scientific inquiry is ultimately a reflection of our shared humanity, an exploration of the unknown that unites us in our quest for understanding.